Welcome to Center of Math's Tricks of Integration. For today, we're going to look at integrating using derivatives. So really, we're going to be making use of this here, where we have some function of x and t integrating dx from a to b. So we're going to be making use of that. In certain cases, we can switch the derivative and the integral. So we say this is equal to the partial of f of x d with respect to t, and integrate that. So these two are equal. This is true. Normally we want this function and its derivative partial to both be continuous in domain. To prove this, in specific cases, that's something you might see in a real analysis course. But for our purposes, we're going to assume that this holds. So we're going to consider the integral of x to the t minus 1 over natural log of x dx from 0 to 1. So this problem could maybe be presented, if we find the integral of this in terms of t, we solve many whole class of integrals. Like this is x squared minus 1 over natural log of x cubed minus 1 over natural log of x. We know the value for any t. So using what we previously saw, we're going to differentiate both sides with respect to t. So differentiating with respect to t, and knowing from our previous thing, we can pull in the derivative, make it a partial derivative. Derivative of x to the t is just natural log of x times x to the t. So these two natural logs cancel out, and then it becomes a lot simpler. Integral of x to the t is just 1 over t plus 1 times x to the t plus 1. We're going from 0 to 1, so our final result is 1 over t plus 1. So we got the derivative of a as a function of t is 1 over t plus 1. But note this, after taking the derivative of t, we can integrate again. But note this integral is much easier than our original thing. So our derivative of a of t is 1 over t plus 1. If we integrate this with respect to t, this just becomes natural log of t plus 1 plus some constant. If we set t equals 0, note that x to the 0 is 1, 1 minus 1 is 0. So a of 0 is equal to 0. I'm plugging in t equals 0 here. Natural log of 1 is 0. So a of 0 equals c, which equals 0. So our constant is just 0. And so we end up with our result. A of t equals natural log of t plus 1. So for example, if t was 2, we want to integrate x squared minus 1 over natural log of x dx from 0 to 1. Our answer would be natural log of 3. One more example. So another example, if we want to try to integrate from 0 to infinity, sine x over x dx. So here we can introduce a parameter. We can say a as a function of t is the integral from 0 to infinity e to the minus xt times sine x over x dx. And so this a of 0 just gives us back our original integral. So taking the derivative of both sides, a prime of t is e to the minus xt times sine x dx, because we just have a minus x that comes down. Yeah. So a prime of t is e to the minus xt sine x dx with a minus. This can be integrated by parts. So what we end up getting is 1 over 1 plus t squared times e to the minus tx cosine x plus t sine x from 0 to infinity. And this just equals negative 1 over t squared plus 1. But we can know that this is the derivative of arctan. So we almost have our answer. We have a of t equals negative arctan t plus c. So if we let t go to infinity, this thing will slowly go to 0. Arctan will approach, arctan of as t goes to infinity should approach pi over 2. Yep, pi over 2. This goes to 0, so we get c equals pi over 2. So we have c equals pi over 2, so a of t equals minus arctan t plus pi over 2. Our original integral is we get by plugging in t equals 0. Arctan of 0 is just 0. And so we get a of 0 equals pi over 2. Or this integral from 0 to infinity, sine x over x dx equals pi over 2. And that's 2 examples. Thanks for watching. If you like this video, please check out the rest. Check out senatormath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.